Welcome to this video where I'm going to talk about some research I've recently done in collaboration with some of my collaborators. Namely, this work I'm talking about today is done in collaboration with Riccardo Balaben, Alessandro Astolfi and Luca Sakarian. And in particular, I'm going to talk about work published recently in Automatica here on orchestrating onboard sensors for global hybrid robust stabilization of unicycles. And the talk is mainly split into two parts. I will first kind of give a bit of a background, discuss the setting, discuss hybrid systems and Lyapunov stabilities, all targeted to the application which we are considering in the second part of the talk, namely targets at stabilization of unmanned ground vehicles. And then on the last slide, I will give some content on how this could be extended and how we have recently extended this work in other submissions. Okay, so what's the motivation of this talk here? Well, we consider we have a mobile robot and a target position or target pose here highlighted visually on this slide. What we could do next is to introduce a certain coordinate system here, considering a coordinate system with position P1 and P2. We could have some external sensors in terms of a ground truth system here highlighted through these two cameras, and we could have GPS highlighted here so that we know at every time step where our robot is currently located. Then many applications, this is represented using Cartesian coordinates in terms of the position and the orientation of the robot, then defining the pose of the robot here. In this work, we focus on a slightly different setup. Namely, we focus on camera-based coordinates. So instead of position and orientation with respect to the final target orientation, we take as coordinates the distance and the bearing to the final position, and then in beta here the parameter theta is encoded. And we also use different sensor measurements. Namely, we assume we have a camera here mounted on the robot, a depth camera, giving us exactly the distance and the bearing angle alpha. So instead of the setup highlighted here on the left, we will be focusing here on the setup highlighted on the right, but then also see what kind of conclusions we can draw from the results here on the right. Because there is a coordinate transformation that allows us to go from the Cartesian coordinates to these camera-based coordinates. And from this coordinate transformation, we can more or less immediately conclude convergence properties. Namely, if R and alpha are going to 0, that means that the position P1, P2 has to go to 0. And if beta is going to 0, that implies that our angle phi here has to go to 0 as well. However, this coordinate transformation is not a homeomorphism, but we can still conclude these convergence properties. Okay, now we are interested in global stabilization, so reaching from an arbitrary initial position of the robot, an arbitrary target position or an arbitrary target pose, But one thing we need to be aware of when we then look at controller designs is that in these problems, discrete or discontinuous control actions usually arise, which means we cannot rely on continuous controllers for this task. So as an example here, we might need to make the decision if we want to go forward or backward. A slightly different application, but intuitively where a similar problem arises would be in obstacle avoidance, and then reaching a target position, we want to avoid an obstacle from the left or the right. So main conclusion here is that, well, we simply cannot rely on continuous control actions. We have to consider discontinuous controller designs. And well, there is in general not a problem in using discontinuous controllers. So here, just illustrated, if we have this decision left or right, well, then here we can simply make the decision at one point and then have this obstacle avoidance here, so one possible solution. However, this is in general, without additional augmentations, only a good solution if we don't have perturbations, because if we have perturbations here added as disturbances, well, then we might get chattering in our solutions where we switch between the left and the right solution, and ultimately, ending up getting closer and closer to the obstacle instead of actually avoiding it. And again, similar decisions or similar situations can occur here when we are switching between forward and backward moving, if we have perturbations or disturbances and are not careful in the implementation of the discontinuous controller. So, takeaway message here would be we want to implement a discontinuous controller or propose a discontinuous controller, but we need to do it in a robust way to ensure that we have robust global asymptotic stability ultimately. And just a bit of additional literature. I'm not getting into detail here, but if you want to look up additional literature covering parts of the things I've just discussed. So the intrinsic limitations here in the non-existence of continuous controllers was initially discussed in this paper by Brockett in 82, and then there are a couple of works discussing discontinuous controller designs or avoiding the problem of discontinuous controller designs by using instead path planning and tracking. An approach which we are going to follow here is closely related to this work here, where we unite different controllers, not in terms of local and globally, but simply trying to combine different controllers and ensuring that overall then we get the properties we are after. Okay, but before we can get there, we, as mentioned before, we are going to use hybrid system theory to essentially give us a rigorous method to describe the switching between different control laws. So here, just a kind of brief introduction of the tools we are going to need and the way we are going to use them, relying on the terminology and kind of language used in the book by Thiel, Goebel, and Sanfelice. So what is a hybrid system, or how is it motivated? Well, we can assume that we have a continuous system evolving in continuous time, described through a differential equation. We can also look at discrete time systems, so not evolving through a difference equation. K plus 1 is equal to a function of x of k. And we can visualize the solution either evolving in continuous time t, or as shown here in discrete time, indicated through the index j. Now, if we use a hybrid system, then we can combine these two components in a continuous update and a discrete update, where we evolve according to the continuous time system if our state x is contained in this set C, and we evolve according to the discrete time update if x is contained in this set D. So our system evolves in the hybrid time domain now with t and j as time arguments, and we have these two equations where simply the state and the sets C and D decide which function f or g we are going to use to calculate the evolution. So a bit of terminology then. Well, so we have these four components: flow map, flow set, jump map, and jump set, defining the hybrid dynamical system here. The way we are going to use this is by introducing discontinuous actions, by introducing a logic state variable which takes on values -1 and 1, meaning, for example, forward or backward, left or right. So this can be encoded in this logic variable here. And then we evolve according to continuous time dynamics, simply relying on the fact that either q is equal to 1 or -1. We evolve according to different dynamics, f plus and f minus, and then we need to potentially update q if our state x is in a particular set or domain. Okay, and one thing we essentially get for free if we design our closed loop system, so closed loop system here represented through this hybrid dynamical systems appropriately, if we ensure by design that C is closed, D is closed, and F and G are continuous, then we satisfy the so-called hybrid basic conditions, and then we know that if we can show nominal stability properties, so global asymptotic stability, then we get robustness essentially for free. And again, so this is this corresponding theory is developed in the book mentioned up here. Okay, so the actual goal we are after and what we need to do to achieve that goal, summarized on this slide over here. So our goal is to stabilize a forward invariant compact set A. And we assume we have given a dynamical system, so representing the dynamics of our robot. We want to design a hybrid system now here, and in particular the controller kappa x, this discrete time update, and the set C and D, such that our forward invariant set A is globally asymptotically stable. To do that, we rely on Lyapunov methods. So again, we want to choose the controller, we want to choose G, and then we need to find a positive definite radially unbounded function, the Lyapunov function, which decreases according to the continuous dynamics and whenever there is a jump. And if we can find these components, kappa, G, and v such that this is satisfied, well, then we have proven global asymptotic stability. It is sometimes too restrictive to assume that we actually get an actual decrease, so less than 0. As it turns out here, in this work which I'm presenting here, we were not able to show a strict decrease. Then it is actually sufficient to have less or equal to, and then use additional properties of the solutions of the dynamical systems one can rely on. So now we are in the position to focus on the actual application we are after, namely the controller design for our unmanned ground vehicle. Okay, and as already introduced in one of the first slides, we are considering these mobile robots controlled in principle by controlling the left and the right wheel, but through a simple coordinate transformation, we can then assume that we are assigning the speed and the angular velocity omega, and we can work with the standard kinematic equations shown here. So position and orientation, and then our inputs v and omega. But as also already mentioned before, we are going to use the coordinate transformation shown earlier to work in camera-based coordinates. So instead we are looking at the dynamics down here in terms of r, beta, and alpha, and the corresponding transformed inputs u. We assume that our angle alpha here is bounded, namely by the field of view of the onboard camera here on the robot. And yeah, so this highlights the position or pose of our robot, while red indicates the target position or target pose. Okay, now let's start with the controller design. We have our dynamics. Then what we can do as controller designs, at least locally, is using more or less standard methods to design local controllers based on camera measurements R and alpha, to design a controller that locally pre-asymptotically stabilizes the set A phi here, meaning it ensures that R and alpha are equal to 0, but we don't care about the final orientation, meaning beta might be unequal to 0 or phi might be unequal to 0. Similarly, or just quickly then, this relies on the local Lyapunov function here. So by designing or by looking at this Lyapunov function, we can design this corresponding controller here with certain properties. If we also want to stabilize the final orientation, meaning beta, want to achieve that beta is equal to 0, then we can look at this Lyapunov function here, deriving this corresponding controller with gains kr, k beta, k alpha, and again obtain pre-asymptotic stability here. So pre-asymptotic stability, that's also maybe one point I should clarify here. So pre-asymptotic stability is used in hybrid systems to state that we don't have necessarily asymptotic stability, because some solutions of the system might not exist for all times t, and these are excluded from the analysis. So pre-asymptotic stability means that all solutions that exist for all times t bigger than 0, they have to converge to our set here, our target set here, but solutions that don't exist for all times t we don't have any restrictions on them. So that's the interpretation here in this context. So that's also highlighted here on the bottom of the page. So we have this assumption as well that we assume that our angle alpha is bounded. So if we hit this bound, then solutions in our interpretation don't exist anymore. And when might that happen? Well, or when might that happen, and why are the results only local? Well, the target might not be in the field of view of the camera, meaning, yeah, if we start like this, the controller derived so far doesn't help us. And secondly, it's not shown here, but even though the target position or orientation might be in the field of view at some point, it might not be in the field of view along the whole trajectory. So that's also where solutions don't exist for all times t. So to now achieve global asymptotic stability instead of just local pre-asymptotic stability, we need to combine camera measurements from different cameras. So that's highlighted here. If we have multiple cameras with an overlapping field of view, then we can group them into forward-facing and backward-facing cameras, and then have these two groups here. And for simplicity, we assume that we then only have two cameras, but the setting can be extended to more than two cameras, where we have one forward-facing, one rear-facing, and we have an overlapping field of view. This means, so this represented now here in equations, we have forward-facing, rear-facing, and the overlap defined through this parameter delta. And now we also don't have a single angle alpha, we actually have two angles alpha measured slightly differently, leading to the different representations corresponding to forward-facing camera or rear camera. So slightly different interpretation now. If we see our target in the front camera, then we try to achieve convergence of alpha f to 0, and we achieve that through forward motion. Whereas if the target is in the rear camera or field of view of the rear camera, then we try to drive alpha r to 0 using reverse motion driving backwards. Another visualization now, but now the first step of combining these two scenarios. So now we have two coordinate systems differing in terms of the angle alpha, and both of these alphas are constrained to a bounded domain. And I corresponding to either f or r, and we can write down the corresponding coordinates, the corresponding dynamical systems, where we observe, well, we actually the only difference we have is here in the signs in front of r dot and alpha dot, so that the signs are essentially flipped. Similarly, we can look at the local control laws introduced earlier, where we also see that the only difference we have in the control laws for using the forward or backward motion would be the minus sign or the plus sign over here, which means if we introduce our logic state variable, q being either +1 or -1, corresponding to ZF or ZR, we can augment our original state. So adding q as an additional variable, so that our state is ultimately 4-dimensional. And we can introduce then the dynamical system of the robot corresponding to the original dynamics of r dot, beta dot, and alpha dot, and then additionally including q dot here, where we have additionally now included q in the first and the third equation here, representing the selection of -1 or +1 front or rear. And similarly in the controller, we can simply have this plus or minus sign represented through the q, the logic state q here. And if we are using these continuous time dynamics, then we set q dot equal to 0, meaning we are not changing the controller selection and the coordinate selection, and simply have that at 0. And when are we using these dynamics? Well, we use them as long as the target is in the field of view of our camera, meaning when alpha, the norm of alpha or the absolute value of alpha satisfies this inequality here. When do we switch? Well, we need to switch if we lose the side of the target for one particular camera. So if this condition here is satisfied, then this defines a component of our jump set D. And then we need to update our parameter Q, so from -1 to 1 or 1 to -1. And we also need to update alpha, but R and beta stay the same. And in this case, then hopefully it also becomes clear what the role the delta plays here. Namely, it's defining a hysteresis region between the switches of the camera, giving some kind of robustness. The larger delta is, the later we switch, but then also giving robustness. So this is one component of the jump set D, introduced so far. So the camera switch. We also might need to reset the orientation if the angle beta is getting too large. So if beta is getting too large, namely larger than 3/2 pi plus delta, then we are also going to reset beta as indicated here, switching between one of these two values. And this then defines our overall jump set as a function or set valued map of our augmented state Xi, where we have a differential inclusion now, where if we are in the intersection of the two jump sets, then we might have to, or then we can, or it's arbitrary which update we are going to use for the jump map, and otherwise we use the updates depending on either G alpha or G beta. Okay, so with these definitions and illustrations, then we can formulate our overall closed-loop hybrid system. So now we have seen how to define F, G, C, and D. We can more or less use the same Lyapunov function as before in the local controller design. But then if we use this Lyapunov function, then we can show that all solutions jump at least once from the set d alpha. So here we were not able to conclude a strict decrease of the function v. So that's why we needed to introduce this initial lemma with the additional property here. But overall, we can show with this Lyapunov function here that if we are only interested in stabilizing the position, so driving r and alpha equal to 0, well, then we obtain here global asymptotic stability. And if we additionally define the third gain k beta larger than 0, then we get stability of the overall pose of the robot, so r, alpha, and beta are going to 0. And so that was the component that was missing in the local controllers. Here all solutions are forward complete, so all solutions exist for all time t bigger or equal to 0. And here, yeah, just some illustrations how these solutions look like. Now either with forward or backward motion for the first controller, focusing on this result. And similarly, if we also want to drive beta to 0, illustrations down here. Now, as pointed out before, if we have these hybrid basic conditions satisfied, which is the case in our setting, then we can even get robust asymptotic stability properties for free. And the stability properties, or the robust stability properties that we can handle here include different components. So the first one we could look at is measurement errors in the feedback, which would mean here we include disturbances here in the feedback. So this, I have to point out, is potentially a bit sloppy. So it's a ball around mainly the components of x, not directly psi. And then with a positive definite function here, mu of psi. We can also take arbitrary external perturbations into account, affecting now the continuous dynamics and the discrete dynamics. And in this case, well, yeah, we have differential inclusions here, or difference inclusions here to consider. We can also argue with uncertainties affecting the switch time. So if we switch too late or too early, that's also not a problem if the perturbations are sufficiently small. However, if we now go back to the initial slide where we discussed the differences between polar coordinates and Cartesian coordinates, if we now want to apply the results from which we derived in polar coordinates and apply them to the Cartesian coordinates, there are some details we need to keep in mind, and where robustness properties are not completely preserved. So first, what we can conclude is if we have asymptotic stability in the polar coordinates, what does that mean for asymptotic stability in Cartesian coordinates? So we get convergence, meaning if we express our state in Cartesian coordinates and then consider the coordinate transformation, then we get that the norm of x is upper bounded by the norm of z, meaning z going to 0 also implies that x has to go to 0. So we have attractivity here. But what is not implied is that if x is 0 is less than a given delta x, that does not imply that z of 0 is upper bounded by delta z. In particular, large z0 can lead to overshoot in the angle beta. And the problem here, or not directly problem, but the missing piece that's simply not satisfied for this coordinate transformation is that we don't have a homeomorphism when we are looking at the coordinate transformation. Meaning, if we are looking at a ball, if we are looking at the coordinates here, r, beta, and alpha, and then the inverse to get back to the Cartesian coordinates, then we see that in particular the angle alpha here is not, can take any value of minus pi to pi, even if alpha is arbitrarily small here. So in summary, stabilization in polar coordinates guarantees convergence in Cartesian coordinates, but not necessarily stability. That also means that some perturbations in some directions can be tolerated, but other perturbations affecting the angle alpha, for example, are troublesome in Cartesian coordinates. Okay, and this essentially concludes the presentation here. Just want to highlight that we have recent extensions on this design, where we are looking at unmanned surface vehicles, published in these two papers here, a CDC paper and then a publication in IFAC Nonlinear Analysis and Hybrid Systems.